Welcome to lecture series on digital electronics under EPG Pathshala. This module is designed to understand programmable logic devices based on read-only memory, that is ROM. We are already aware of there are different types of ROMs, like you have a maskable ROM, that is MROM. Then we have PROM, programmable ROM, where PROM can be programmed by the user, whereas MROM can be programmed by the manufacturer. When we talk about EPROM, it is erasable programmable ROM. Now, user can program this memory whenever the program is to be removed or changed or upgraded, whereas in case of E2PROM, it is possible to erase the memory contents electrically. There is no need to erase the contents as a whole. Whenever we talk about erasing the contents of the memory, we can select the addressable location and that can be erased. So, this variety of memory devices can be used as programmable logic devices. When we talk about any Boolean function can be expressed in terms of some kind of a truth table. And when we prepare the truth table consisting of some n input variables and we have m output variables, naturally it is expressed in terms of sum or product form. Now, whenever we talk about sum or product forms, naturally the product terms are the min terms. So, whenever we talk about min terms, we have to generate some kind of a product. Now, this product term can be summed together by using some kind of a hardware. So, if you look at the internal structure of ROM, basically what we require is some kind of a address decoder. The second part that is required is array matrix and the third part is OR gate. When we talk about address decoder, naturally it consists of some kind of AND gates, and this AND plane is permanently programmed. So, that is why this decoder can generate all possible min terms corresponding to n variables. So, when you have n variables, there are 2 raised to n corresponding product terms, those could be generated. The array matrix consists of rows and columns. The rows are the outputs of the decoder, whereas the columns are usually connected to the pull-up register. These pull-up registers are connected to VCC or logic 1, and whenever we talk about such kind of a configuration, usually we take the output from the OR gate. So, whatever the terms those are present in the sum, those min terms are added together and the output is taken from the OR gate. So, we have AND and OR plane. OR plane is a programmable and user can program it whenever that is required. So, this concept will be explored in this module. Now, to demonstrate the use of ROM as PLD, we will take certain examples. The first example that we will be exploring is use of ROM as function generator. The second example that we will consider is to generate a square of the given number, it is called as a square generator. The third example we will be exploring is BCD to X-ray3 code generator. Similarly, we can have n number of such examples wherein there is a need to have some kind of a code conversion, maybe BCD to 7-segment code or maybe BCD to binary or BCD to ASCII and so on. So, we can have n number of such examples, those could be using ROM as programmable logic devices. Let us explore now the word of ROM as a PLD. Let us talk about learning objectives of this module. In this module, initially the basic architecture of ROM will be studied, so as to understand how a ROM can be used as programmable logic device. Second, to understand diode matrix ROM. Third, the use of ROM as PLD would be explored by taking few examples. Later, the advantages and disadvantages of ROM as PLD will be studied. Let us now explore the word of read-only memory. The ROM is characterized by 3 important parameters: writability, storage capacity and non-volatile nature. It is a programmable memory and the contents of the memory are decided by the user. It is also non-volatile memory, where the contents of memory are not lost even after removing the power. The time required to access the memory is uniform irrespective of the position of the addressable location. The memory has random access property indicating delay is uniform for all addresses. There are 5 basic ROM types. ROM, that is read only memory, which is basically a mask ROM. Then PROM, that is programmable read only memory. EPROM is a erasable programmable read only memory. E2PROM is electrically erasable programmable read only memory, and last flash E2PROM memory. Programming ROM means writing the data into the address location. ROM can be programmed once or many times depending on the type of ROM. A typical ROM structure is shown here. Typical ROM contains M by N memory, where M indicates number of addressable memory locations and N indicates number of data lines or storage capacity of each addressable word. ROM is basically a combinational circuit with k inputs and n outputs. There are k address lines, that is 2 raised to k addressable memory locations and n data lines. Read bar, write bar and CS bar are 3 control signals of the ROM indicating read, write and control signals. The ROM stores 2 raised to k words of n bits each, or the ROM stores k input, n output truth table. These are the 2 viewpoints to look at the ROM. Let us consider the truth table as shown in the figure to understand this concept. There are 2 address lines which provides 4 possible combinations of addresses which are labeled from 00 to 11. This indicates there are 4 different addressable memory locations with storage capacity of 4 bits each. This indicates that such truth table there is a requirement of 4 by 4 ROM. This ROM stores 4 bit words or stores 4 functions of 2 input variables. The basic architecture of ROM is shown here. Internally, the ROM has 2 main sections. The first section is the decoder, which is used as address decoder. It is basically k line to 2 raised to k line converter. The second section is the memory array, that is matrix consisting of 2k words by n bits. Let us now discuss the diode matrix ROM. Diode matrix is formed to visualize the implementation of factory programmed ROM. ROM usually consists of an address decoder, a specific physical setup, a grid of wires used to implement read only memory. In this 2-dimensional wire grid, each connection or interconnection of wires either has a connecting diode or no diode. In this diagram, 2 to 4 line decoder is used to activate one of 4 rows in response to 2 address lines. There are 4 data lines which forms the columns of the matrix. The data lines are connected to plus VCC through pull-up resistors. The output of data lines are taken out through inverter. This ensures that by default the output bits are all zeros. Bits are programmed by adding a diode between the given data line anode and address line cathode. When one of the address lines is made low, the corresponding data line will only be pulled low if a diode is present. Let us now add diodes to the desired position to store the data at various memory locations. When the memory address is 00, the data stored in the ROM is 1010. Thus, diodes are present in the first and third column. These diodes are turned on as row 0 is activated, that is 0. This will make D3 as 1, D2 as 0, D1 as 1 and D0 as 0. When the memory address is 01, row 1 is low. The data stored in the ROM is 0100. For address 01, the row 2 is activated and data stored is 0001. In the memory addressed 11, row 3 is activated and the contents of data are 1000. It is important to note that transistors or MOSFETs can also be used as switches in the ROM matrix to record the data. Let us now discuss how ROM can be used as PLD. For implementation of PLD, what we require is simply sum of product form. The internal structure of ROM consists of 3 parts: address decoder, memory array and OR gates. The first block is address decoder in memory. For each binary address, input pattern produces exactly one of the horizontal line of the address decoder. In the example, 2 to 4 line decoder is required to control 4 word lines or rows corresponding to 4 memory addresses. Basically, the decoder provides the product terms. Let us understand the internal logic of 4x4 ROM. It consists of 4 words of 4 bit each. To access 4 locations, we have to use 2 input lines. The address can be 00 to 11 for the ROM. The 2 inputs are decoded into 4 lines with the help of 2 line to 4 line decoder. Each output of the decoder represents a memory address. The 4 outputs of the decoder are connected to each of the OR gates. Each OR gate has 4 inputs. As each OR gate has 4 connections, there are 4 OR gates are required. Hence, there will be 4x4 16 internal connections. All these interconnections are programmable. The programmable interconnection is also popularly known as cross point. Many times a simple method is to use fuse link. The fuse link is normally intact and connects horizontal and vertical line. Presence of link is equivalent to one of the logic, maybe say logic 1, and absence of link is referred to as logic 0. Let us now take example to demonstrate how ROM can be used as programmable logic device. Implement the following 2 combinational functions using a ROM. F1 is a function of AB is equal to sum of minterms 1, 2 and 3, and F2 is a function of AB which is equal to sum of minterms 0 and 2. The first step in the implementation is to determine the size of the ROM that is required. ROM has 2 inputs A and B, then k is equal to 2, hence we require 2^2 4 locations. The number of outputs, that is n is equal to 2. Let us label outputs as F1 and F2. Each memory location can store 2 bits. Thus, the size of the ROM can be 4x2 bits. Let us specify the ROM data contents so that it can be programmed into the ROM. As F1 has 3 minterms corresponding to 1, 2 and 3, the truth table for F1 contains 1 for each of these minterms. Similarly, minterms for F2 are also written in the truth table for 0 and 2. The desired ROM is having capacity 4x2 bits. Let us consider the address lines A0 and A1 as 2 inputs, namely A and B. The 2 to 4 line address decoder generates all 4 combinations. At each location, the data is decided by the values of F1 and F2. For address 00, the contents of memory are 01. Hence, link is shown for F2 only. For address 01, the contents of memory are 10. Hence, link is shown for F1 only. For address 10, the contents of memory are 11 bit. Hence, the cross links are shown for both F2 and F1. For address 11, the contents of memory are 10 bits. Hence, the link is shown for F1. Consider example 2. Implement the following function in a ROM. F1 is equal to A bar and F2 is equal to A bar B plus AB bar. The first step in the implementation is to determine the size of the ROM that is required. ROM has two inputs A and B, then k is equal to 2. Hence, we require 2 raised to 2, that is 4 locations. The number of outputs, that is n is equal to 2. Let us label outputs as F1 and F2. F1 is equal to A bar, which can be expanded to get min terms as F1 is equal to A bar B bar plus A bar B, and F2 is equal to A bar B plus AB bar. As there are two min terms present for each function, the binary 1 is returned when the term is present. One can even show the programming of ROM using a decoder and matrix array. Let us consider the third example. Design a combinational circuit to generate a square of the given number and implement it using ROM. Let us prepare a truth table of square generator. Consider a 3-bit number as the input to the combinational circuit. These inputs are labeled as A, B and C. The binary combination of input gives decimal numbers 0, 1, 2 till 7. Let us obtain the square of the numbers in decimal and write it in a separate column. The squares are 0 for 0, 1, 4, 9, 16, 25, 36 and 49 corresponding to the input. There are 6 bits required at the output of a combinational circuit to implement the square generator. Let us write the square of the number in binary. For example, 0, we have all bits zeros. Square of 1 is 0, 0, 0, 0, 0, 1. Square of 2 is represented as 0, 0, 0, 1, 0, 0. Square of 3 is represented as 0, 0, 1, 0, 0, 1. Square of 4 is represented as 0, 1, 0, 0, 0, 0. Square of 5 is represented as 0, 1, 1, 0, 0, 1. Square of 6 is represented as 1, 0, 0, 1, 0, 0. Square of 7 is represented as 1, 1, 0, 0, 0, 1. For implementation of square generator, the desired ROM requires a capacity of 8 by 6 bits. The address decoder 3-line to 8-line decoder will accept 3 inputs ABC. The address decoder generates 8 output lines acting as rows. The number of columns in the matrix is decided by the number of outputs of the combinational circuit. In this case, there are 6 outputs Y0, Y1 up to Y5 generated from OR gates combinations. Let us refer to the truth table and put a cross link in a matrix. Wherever the output is 1, here we can put a cross indicating logic 1 for all outputs as shown in the diagram. We can repeat the process for all different rows. Consider another example. Design a combinational circuit for conversion of BCD code into XS3 code. Implement this design using a ROM. Let us now understand how ROM can be used as PLD. Let us start with a BCD number which is represented by 4 bits and 4-bit XS3 code as outputs of the combinational circuit. First step is to prepare the truth table for this code converter. Let us consider the numbers represented by ABCD provides the input BCD code and Y0, Y1, Y2, Y3 provides the output XS3 code. Let us consider the BCD number 0000. The XS3 code is the addition of 3 to the BCD code. Thus, we get 0011 as a XS3 code for BCD 0. In this truth table, XS3 code is obtained by adding 3 to the BCD code. As the numbers of inputs to the truth table are 4, there are actually 16 possible combinations in binary, but in BCD we restrict ourselves to only 10 possible combinations corresponding to binary coded decimal numbers. So, there are 10 different memory locations, those are required in the memory. Each location is capable of storing 4-bit data which is addressable by the ROM. Let us now talk about advantages of ROM as PLD. ROM can implement any function because all the minterms are available. Second, ROM based design is easy to implement as there is no need of simplification or minimization of logic functions. Third advantage is that truth tables are implemented directly. Fourth, design can be changed or modified in a programmable ROMs. Fifth, ROM based PLDs are faster than discrete SSI or MSIs. And last advantage is the reduction in the cost of implementation. There are few disadvantages of ROM as PLD. First, design becomes complex for a large number of inputs n. Second, it is possible that there is a underutilization of complete ROM circuit for simple applications. Third, increase in address size with increase in number of input variables. Fourth, increased power requirement. And last, it does not support multi-level circuit as no outputs are brought back as inputs. Let us summarize few important things from this module. Let us consider certain take home points. First, we have studied basically the architecture of ROM. The architecture ROM indicates there are few address lines, data lines and control lines. The number of address lines could really decide how many addressable memory locations we can have in the ROM. And when we talk about data lines will indicate what is the storage capacity of each memory location, whereas the control lines will decide whether we are interested in reading or writing the information. When we talk about the internal structure of the ROM, it consists of 3 major parts. The first one, address decoder, the second one is the array matrix, and the third one is basically the array of OR gates. Now, in addition to that, we need to have some kind of a fusible links which will decide the connections between rows and columns. Now, when we talk about array matrix, the rows are basically generated through the address decoder. Only one of the row is enabled at a time depending upon the address that is selected, and the corresponding column is really related with the number of storage bits that we can have it at per memory location. Now, all the columns are connected to VCC through pull-up register that will decide the corresponding high state or low state of the column. Whenever we talk about connecting something between rows and columns, we have to have some kind of a fusible link. We have seen that in diode matrix ROM, we can connect rows and column by putting the diode. Presence of diode indicates logic 1, absence of diode is treated as logic 0. In addition to diode, we may use basically some kind of MOSFETs or transistors as a link. But when we talk about traditional ROMs or PROMs, we use some kind of a fusible link. So, whenever user is interested in programming the ROM, we have to use some kind of a cross point. Rather than using dot for the interconnections, we use cross, indicating that it is a fusible link. That means, it is a user programmable link. All PLDs, they use two conventions. When dot is used for the convention, that indicates it is a permanent connection provided by the chip, whereas the cross indicates that it is a programmable link, where user can decide the value of the bit, it could be 1 or 0. In this case, we have studied the example of ROM as PLD by taking few simple examples like function generator, square generator, as well as BCD to XS3 code converter. We can even study several more examples in next module. Thank you.